All right, so we are going to talk about ionic bonds and their compounds that they form today. Lucky for us, we kind of started it last chapter in chapter 7. So an ionic compound is, electrically speaking, it is neutral. We know this from last chapter because we would always balance out the charges so that they would equal 0 when they form the compound. So they are electrically neutral. And they are held together by electrostatic force. And electrostatic force is just a fancy way of saying the positive-negative attraction. So an ionic bond is the electrostatic force that holds ions together in an ionic compound. The strength of this bond is dependent on the magnitude of the charges. So that means that the bigger the charge is, the stronger the bond will be. So a cation that has a positive 2 magnitude will produce a stronger ionic bond than something that has only a positive 1 charge to it. When you look at the size of the ion, that also plays a part in determining the bond strength. The bigger ions will produce weaker bonds. This is because with the bigger ions, the valence electrons that are responsible for doing the bonding are farther away from the nucleus of the other ion. So if we increase the distance, we decrease the bond strength. So sometimes scientists use electron dot diagrams to show these bonds. So if we look at sodium, sodium has the 1 valence electron right here, and chlorine has 7 valence electrons. So the 1 valence electron of sodium will join in on chlorine, so that chlorine has a complete 8. And sodium will also achieve noble gas configuration. And so you notice when they write the compound with the electron dot diagram, sodium no longer has any dots around its symbol. Why would that be the case? Why would sodium no longer, or sodium or any of the cations, have any dots around their symbol? Cora? Yep, so sodium gave off its 1 valence electrons, and the dot diagrams show valence electrons. So sodium technically no longer has valence electrons to show around the dot diagram. So the way that they word it is that the energy level that originally contained the valence electrons is now empty. And that emptiness is shown by not writing any electrons around the cations. Here's just another example. However, this example with magnesium and chlorine shows you how you can take 1 cation and bond it to 2 anions. When you look at these dot diagrams of elements bonded together ionically, the anion should show a complete octet or a full octet. So ionic compounds are reported in formula units instead of like molecules. A formula unit is the lowest whole number ratio of ions present in ionic compounds. This is always the empirical formula. This is what you learned from chapter 7, naming ionic compounds. When you write NaCl, for example, you have written the formula unit. So NaCl right here is equal to 1 formula unit. 2 NaCl is equal to 2 formula units. I used to abbreviate formula units FU, and then I figured that looked bad. 1 FU, 2 FUs. Ionic compounds, so this is just some characteristics of ionic compounds. Their structure is referred to as an extended 3D array. And this extended 3D array will alternate cation and anion. This helps to maximize the attractive forces between the oppositely charged particles. And there's a couple ways of drawing them. The first method right here is called the ball and stick method. And the second method here is called the space filling diagram. So in the ball and stick method, these red lines right here are just showing the bonds between the anions. Whereas in the space filling diagram, they don't show or draw the bonds or the positive negative attractions between the two anions. Does that make sense? They save in space. Sometimes this extended 3D array is referred to as a crystal lattice. You'll probably see that word come up a couple times. So when we look at these structures, they sometimes like to assign coordination numbers to an ion. And this is the number of ions that immediately surround an ion of the opposite charge. So the ratio of coordination numbers must exhibit the same ratio as the formula unit. So to figure out the coordination number of sodium, so sodium is shown here in purple. So what is the coordination of sodium? And you would look at how many greens or chlorines are bonded to it. So what would be its coordination number? This is like a counted up kind of thing. And we're going to count 1, 2, 3, 4, 5. And which one are we missing? The up. So the coordination number of chlorine is also going to be 6. Now, if you wanted to look at the ratio of the two coordination numbers, what would be the ratio? 1 to 1, good. 1 to 1. So, it is important, if you want to check that you have the correct coordination numbers, what is the formula for sodium chloride? NaCl. Does your ratio of NAs to Cls match in both? Yeah. Yes. When you look at the ratio of coordination numbers, it has to be in the same ratio as the formula unit. Does that make sense?
So if they give us like the name, can we just like do that, but then like write it out on the bottom so you know what you know?
Right. However, be careful, because if it asks for the coordination number, it's not necessarily going to be the same digit as would be found in the ratio. Does that make sense? Because the ratio is going to be in lowest terms. So, can practice again. This one's maybe a little clearer to see it. So, looking at cesium, cesium is this center one in orange. Brett. Okay. What would be cesium's coordination number? 8. Good? Okay. And then coordination number for chlorine, which would be in green. 4, 5. Another 5.
8.
Oh, an 8. Who said 8? Alexis? Okay? So, we've got a lot of numbers up there. What if we, to figure it out, which number we like best? What's the formula unit for cesium chloride? Cesium's charge is +1, chlorine's charge is -1, so it would be cesium chloride. So what does our ratio have to be? 1 to 1. So what does our coordination number for chlorine have to be? It has to be 8. Okay, so there's a couple methods to help you figuring out coordination numbers. If you can figure out one for sure or that you're very confident in, you can then use your formula units to determine what the ratio is, which will then help you determine the coordination number of the second element. So it's kind of a work backwards method. Okay, another practice. What is the coordination ratio for titanium 4 oxide? Titanium is the gray molecule, and oxygens are the red. So what is your coordination number for titanium? I would look at this center gray one right here. 6. 1, 2, 3, 4, 5, 6. Good. So then what would be your coordination number for oxygen? Oops, why did I put an I there? Oxygen, 1, 2, 3. It even shows you in 2 places here. So 3. So then what would be your ratio? 2 to 1. And does this make sense for the formula unit for titanium 4 oxide? Titanium's charge is what? +4. Oxygen is -2. So to balance it out, we need 2 oxygens. Titanium O2. Does that make sense? Yep. Very good. All right, so then just some physical properties of ionic compounds. Their shape is very geometric. It's very regular, repeatingly patterned because of the positive, negative, like the repulsion and the attractions of the different positives and negatives. Ionic compounds will get their color from transition metals. Transition metals are typically more colorful when they're just by themselves even. The strength of an ionic compound will come from its many electrostatic attractions in the crystal structure. So essentially, every ion is either being attracted or repulsed, pushed away, whatever, from the next one to it. This gives ionic compounds very high melting points. This is because in order to melt something, you need to break bonds. And so it requires a lot of energy to break the bonds between ions in an ionic compound. An example of one of these high melting points is table salt. Its melting point is 800 degrees Celsius. So to get table salt to melt, you have to heat it up to 800 degrees Celsius. Whereas to get water to melt, which is a molecular compound, you have to warm it up to only 100 degrees Celsius. Ionic compounds are very brittle, that kind of like they're going to shatter if they break. The reason for this is if you apply a force to an ionic compound, it is going to force ions with the same charges to be near each other. When that happens, they're going to want to repel, which causes a shattering effect. So typically, if ionic compounds break, they will shatter, and the breaks will be along clean planes. So you will get very straight line breaks. They're not going to be jagged. It's going to be almost in very nice geometric shapes. The last characteristic of ionic compounds is they have the ability to conduct electricity. So in this experiment, what it is showing is that an electrical current here in plain distilled water will not conduct electricity. This is because water is a molecular compound. Molecular compounds do not transfer ions because ions are not formed in molecular compounds. In this second example, here we just have the solid, and so the positive and negative ions are still being attracted to one another. So there's no movement in the ions. They're still stuck in place. So once we dissolve the ionic compound in water, such as this one, the positive and negative ions kind of separate from one another, and they are now free floating and able to move back and forth between the electrodes up here, which allows a current to move. So when you talk about an electrical current, what that is essentially ions moving. So it is a current of ions. And it depends what kind of ions it is in order to power it up, or whatever device you're trying to power. Some ions will move more freely than others.